Tuition Mobile, quality e-learning experience on the go.
You're welcome back to the class. Our topic today is captioned Modular Arithmetic. Modular Arithmetic. Modular Arithmetic is quite a useful tool in number theory. It can be used to obtain information about solution of specific equations. Okay. Topic modular arithmetic. All right. Okay. Modular arithmetic. Shortly after discovering whole numbers like 1, 2, 3, like you knew from your primary schools, we realized that whole numbers fall into two groups, and these two groups they fall into are called even numbers and odd numbers. Let me quickly define even numbers as even numbers, right? Let me quickly define them as numbers divisible by 2. Numbers divisible, not necessarily divisible by 2, because even numbers can also be divided by other numbers, but I'm using 2 as a case study for our study today, so that we can define even numbers as numbers when being divided by fellow even numbers, or even odd numbers can give no remainder. And using 2, we can define even numbers for this class as numbers when being divided by 2 will have no remainder. Alright, okay, and in my set of divisible numbers by 2, I have the following numbers. I have 0, I have 2, 4, 6, 8, and so on. These numbers, if being divided by 2, wouldn't have a remainder, and so we call them even numbers. And then I'll also define odd numbers as numbers using 2 also as our point of contact as our case study. I will also define odd numbers as numbers if divided by 2 would give remainders. Okay, and so since they cannot be divided by 2, we can say that odd numbers are not divisible by 2, or either when they are being divided by 2 they give remainders. Alright, odd numbers. Alright, not divisible by 2, not divisible by 2. Okay, and my set of odd numbers, I have the following numbers. I have 1, I have 3, I have 5, I have 7, and so on. There are other odd numbers. I think within the primary school range you should have known these two. Alright, this distinction is important because from here we notice the properties of a number. Okay, that means a number could be even, a number could be odd, and not just the number itself. Even an odd numbers, there is bit some relationship, and I can point out the relationship there is bit. All these are for the purpose of this study. Okay, relationship between even and odd number. Odd numbers. Alright, I can list these relationships as follows, and list them as follows. The number one relationship here is that when you multiply even numbers by other even numbers, okay, you will always obtain an even number as the outcome. Okay, and then number 2 states that when you multiply odd numbers by odd numbers, okay, the outcome will be odd numbers too. Okay, and then the third property there is this, that when you multiply even numbers by odd numbers, Okay, the outcome will be what? Even numbers. All right. So you can take any illustration you like, because as for me, I'll go back to my even number side, and then I can take an example like 2 times 4 is 8, and you can see it is still even number. Okay, and then I can use the same analogy for this. I can say odd numbers 3 times 7 to give me 21, which is still odd. I can go to the third property, the third relationship, and I can say choose any even number. I could use 3 and 2. Okay, you see it's given me even. Or I could use 7 and 4. It will as well give me an even number. Right, to the next slide. Right, these rules are general as they work at the same property level. Okay, now assuming we pick up numbers from our sets of even numbers and odd numbers too. Odd numbers, I think sets of integers. Okay, we could say that a number which is divisible by 3 without giving a remainder is a true even. For instance, if I have this set, being divisible by 3, 6, and 9, and the number continues, numbers that are divisible by 3. Okay, I could say that these numbers are 3 even. Alright, no, you don't get deceived by this. It's just an analogy. I want you to understand something from this instance. Okay, in like manner too, a number not divisible by 3, we could say the number is 3 odd or third. I could choose numbers on these sets like 1, 2, 4, 5, 7, 8, and so on. You see, these numbers are not divisible by 3. I could call them third, 3 odd, because these are numbers that when 3 divides them, okay, you will always have a remainder. But the first one are numbers that when 3 divides them, you will not have any remainder. But at this point here, when 3 divides, there will always be a remainder. So I call them third because 3 cannot divide them without leaving a remainder. Remember what we defined even numbers are. So use the same application for this. So thus, this looks weird, but it's workable. It looks weird, but it's workable. You have to notice that a number like 4 is one way from being 3 even. Okay, what we are saying actually is this, that a number like 4, when 3 divides 4, when 4 is being divided by 3, okay, you find out that what you have is one whole number 1 over what? 3. Okay, which means that the number 4 is one way, it's one way away from being 3 even. I don't know whether you get this. I think, but it's not difficult. It's simple. All you have to do is to reason it this way. Since even numbers are numbers, when being divided, they don't give remainders. Okay, 4 could have been an even number if 1 is removed from 4. Okay, and since if 1 could be removed from 4, it's an even number. We cannot say that 4 is 1 away from being 3 even. All right. Okay, and so we can say in like manner too, a number not divisible by 3 is said to be 3 odd or third. Okay, and we've taken an example for is one way from being 3 even. And assuming we take another example using 5, 5 is also listed on the list of third numbers, and then we take 5. You find out that 5 divided by 3, 5 divided by 3 will give you same one whole number 2 over 3. Okay, you see 2 is the remainder. What it remains for 5 to be an even number, so we can say that 5 is 2 away 3 even. Okay, if 5 could be reduced by 2, it can now be an even number of 3. I hope you understand this. All right, so that is the remainder when you divide 5 will be what? 2. And never mind, we have just made some valuable illustration which will come into play later. Modular operation is the remainder when dividing. It is abbreviated as mod or with a percentage sign. You know, it always comes to play when you are programming. Maybe you want to program modular operation is represented differently from the way it is represented mathematically on your computer systems. All we are saying is this: modular operations has more emphasis on the remainders of the numbers which you divide, and modular operations can be abbreviated as this. Abbreviations for modular operation. Alright, you can abbreviate as mod, or you can write as percentage. This you will encounter most when carrying out mathematical operations. Okay, this you can encounter if you are a programmer, okay, or you want to run programs on your computer system. If you're a programmer, you want to run programs on modular operations on your computer system, you may not really see mod, but when you see a percentage sign, it means modular operation. Now to the next slide. Alright, for the purpose of this class, we shall define an even number as 1 where it's 0 mod 2. Alright, we shall define even numbers as 1 where it is 0 mod 2. And from previous examples we did, using our previous illustration, we found out that 5 mod 3 is equal to 2. Okay, all we are saying is that 5 as the number before it can be even in 3, 2 will be removed. Okay, and that is as good as saying 5 divided by 3, okay, will give you 1, but the remainder will be what? 2. And remember, we said that our interest only lies on the remainders after division. Alright, just like I said, for the purpose of this class, we shall define even numbers as 1 where it's 0 mod 2. That is, it has a remainder of 0. Alright, we shall define even numbers to be equal to 0 mod 2. Okay, all we are saying here is that when you divide even numbers, the remainder will be 0, and also we will as well define the odd number as a number when you divide by 2, the remainder will be 1. So we shall define odd numbers for this class, odd numbers to be equal to 1 mod 2. Alright, and so having this in mind, this changes our aforementioned relationship to as follows. This changes our relationships to as follows, and then the relationship becomes this. What we are saying is that now when even multiplies an even number, okay, it's as good as saying 0 times 0, okay, to be equal to 0. Okay, remember we said that when two even numbers multiply each other, it will give you an even number. Okay, and then the second rule now becomes that when two odd numbers multiply odd numbers too, okay, it implies that, remember, we denote by 1 because we said that the remainder will always be 1, but if it were to be even, the remainder will be 0. And so 1 times 1, what did we say about odd times odd? You find out that we said that when two odd numbers multiply, the outcome will be odd numbers too. And from the illustration we used 3 times 7 here. That's it, 3 times 7. That's the second rule. Okay. And then the third rule states that when even number multiplies an odd number, okay, we can denote, since we've been denoting even numbers as 0 and then odd numbers as 1, and from the rule we said it will always give an even number, which is 0. This is odd and this is even. Alright, so we can as well define the outcome for various other combinations of this relationship, assuming we want to multiply even numbers by even number and then by odd number and then by odd number again. Okay, so what would this outcome be? I will advise you to use two methods to do this. You can do this separately, okay, and then do the two outcomes together. Alright, what happens when even multiplies even? It still gives you an even number. Alright, then bring down your multiplication sign. What happens when odd multiplies an odd number? It gives you an odd number. And then from this point you have even times odd to give you what? To give you even numbers. Okay, so, and we said you can denote even numbers as 0, and in like manner you can denote this as their outcome, and since the outcome is 0, you can put 0 at this point. Okay, you can represent even as 0, 0, odd as 1, 1. Okay, 1, sorry, this should be 0, and then this should be 1. That looks rough anyway. And so that's exactly what we're saying. You can use any other analogy. You can use any other analogy to describe this. You can use any other illustration. That's all we are saying in this sense. And then any other illustration could be, what if you want to determine for other examples? Alright, maybe you want to determine what the outcome will be when an even number multiplies an odd number. What would the outcome be? Like I said, you can take 2 at a time. Even times odd will give you even number. You bring down your multiplication sign, you bring down your even number at this point, and then even times even will give you even. So 0. Okay, let's try one more example 3. Example 3. Okay, on this example 3, I want us to multiply odd times even. Okay, alright, you can take this first 2. Odd times odd will give you odd. Bring down your multiplication sign, bring down your even. Now odd times even will give you what? Will still give you even. So notice that at this point you have even, at this point you have even too. Alright, okay, can we take more examples? Example 4, so that we can draw out some properties from this. You find that you have odd times odd times odd. Let's use this. Okay, they are all odd, and so at this point to the next slide, right, we had odd times odd times odd. Okay, at this point odd times odd is odd. Bring down your multiplication sign, bring down your odd. Odd times odd gives you odd, so the outcome will be odd numbers. Now all you have to note here, you have to note at this point, you have to note that whenever odd numbers multiply each other, okay, alright, the outcomes must be an odd number. It must be an odd number. Alright, but then whenever even numbers multiply each other, the outcomes will as well be even numbers. But one thing I want us to note here is that if there is to know that if there is an even number being multiplied anywhere, okay, no matter the number of odd numbers, the outcome will be even. Okay, just note this too, that if there is an even number affixed at any point, okay, then it means the outcome will necessarily be an even number. Okay, you can try more examples on your own so you can prove this, but from previous examples we did, you find out that wherever 0 comes in, the outcome will always be 0. Wherever 0 comes in, the outcome will always be 0. That is, and you know, we are using 0 to represent even numbers in our class for today. And so modular arithmetic, will be considering modular arithmetic as a representation of time. You know, modular arithmetic is sometimes called the clock maths or the clock arithmetic. Okay, so I want us to consider the modular arithmetic as a clock maths. The modular arithmetic as a clock maths. Right, beautify it a little. All right, and the modular arithmetic is also called the clock maths. I've said this previously, and we shall make explanations on this. We'll be using examples, assuming, you know, different hours of the time. Now all I want you to note here for this class is this. The time we have in our homes, once it gets to 12, the time starts afresh. You know, time moves from 1, 5 minutes, 10 minutes, 20 minutes, 30, 40, 50, 60, and the 60th one, the time starts afresh. Okay, what we are saying is this is your clock at home, and this here you have 12, and here you have 1, and here you have 3, here you have 5, and here you have 6, here you have 7, and here you have 9, and then you have 10. At this point, I could as well assume this to be 11, 2, 4, and 8. I think the time is complete. All right, so all we are saying is your minute hand, and this is our hour hand. Okay, now when the time moves from this point, it rotates. The minute hand keeps moving until it gets to 12, and when it gets to 12, what happens? Counting starts afresh. Okay, at 12, counting changes to 0, 0, and at this point we said the time has gone to what? O'clock. Okay, you know, the clock resets and starts to count time from the beginning. Okay, and so we use this logic for the modular arithmetic. And then what we say is, once it gets to 12, what happens? We can count 1 hour. Okay, once it gets to 12, the time is 1 hour. So we'll be using this logic to work on modular arithmetic. Okay, what we are saying is this: if you are given a number, okay, to a specific mode, take that mode to be the extreme point of the counting where the number resets. All right, take the mode to be the extreme point where the number resets. Assuming we take these illustrations, assuming we take an example, right? We could say, for example, we could say 7 mode. Example 1. You could say 10 mode 7. All right. Remember that when the counting gets to 10, okay, what happened? It resets. Okay, so how many 7s can be found in 10? It could only be 1 7, and so we could say that 10 mode 7 is congruent. The sign means congruent. It's congruent to what? 3 mode 7. Is understood? All right, you wouldn't get this way. But when I use the 12-hour clock to make my illustrations, you will understand better. So all we are saying in the sense is ticks. We are saying in the sense is ticks. For example, if we have, assuming the time now is 7 o'clock a.m. all right, I think this illustration will sound better. Example 2. Now assuming the time at this point, assuming the time right now is 7 o'clock. Okay, I don't mind whether it is AM or PM. All right, the question now is where will the hour hand be in 7 hours? Where will the hour hand be in 7 hours? Okay, how do we find out where the hour hand will be in 7 hours? Assuming the time today is the time at this point in time is 7 o'clock. All right, look at how we do this. Okay, the hour hand, since it is 7 o'clock and the next 7 hours, all right, the solution follows on the next slide. Solution. All right, assuming it's 7 o'clock right now, the next 7 hours we are talking about adding 7 to 7 o'clock, it would be in 14 hours. It will be in 14 o'clock, assuming we are using a clock having more than 12-hour time. So it means in the next 7 hours, the time should be what? 14 o'clock. But then we have all we are using is a 12-hour clock. All we know is a 12-hour clock. So how can we illustrate 14 o'clock in a 12-hour clock? Well, we can't show this on our 12-hour clock. So 14 o'clock so far will look like this. Now look at the logical reasoning. It follows this way. You know, using the modular arithmetic, you could say 7 plus 7 mod 12. We are using mod 12 because our clock is a 12-hour clock. Okay, it's as good as will be equal to 14 because 7 plus 7 gives you 14. Talking about 14 mod 12. Okay, remember what we said previously, that when the time gets to 60 minutes, it restarts. When the time gets to 60 minutes, it restarts. And so the logic follows this way. That means when this time gets to 12, it will restart because all we use is a 12-hour clock. And here the theory of remainder comes to play. The theory of remainder comes to play. We ask ourselves what happens when 14 is being divided by 12. The remainder will be 2. And so we could as well write 14 mod 12 to be equal to this. Okay, when we use this sign, it means congruent. Okay, 14 over 12 to be congruent to 2 mod 12. Okay, and it logically follows that if the time is 7 o'clock now, in the next 7 hours, the time will be 2 o'clock. So all we are saying is that the equation 14 mod 12 could be written as well as 2 mod 12. Okay, good. Since in the next 14 hours the time will be 2 o'clock, and logically it follows. All right, just like I said, so you don't mix things up. When you say this sign, it stands for congruent relationship. Congruent relationship. All right. Okay, we'll take other examples, because I believe with further examples you will come to grab quickly what the topic is all about. We take example 3. Example 3. Assuming it's 8 o'clock now. Assuming it's 8 o'clock now. Where will the big hand be in 25 hours? Where will the big hand be? Where will the big hand be in 25 hours? In 25 hours. Alright, that's the next question. So where will the big hand be in 25 hours? A modular operation, like we said, the solution follows like this too. The solution follows in the same manner like the first one. Alright, and so this becomes 8 plus 25. Remember, it's a 12-hour clock, so it is still mode 12. Alright, 8 plus 25 gives us 33, right? 8 plus 25 gives us 33. Sorry, I think we're saying 8 plus 25 mode 12. Let's move over to the next slide so we can find it very clear. 8 plus 25 gives 33 mode 12. Alright, is also equal to what? 8 plus 25 mode 12. Okay, we look at 33, we look at 12. Okay, 12 dividing 33. How many 12s will you have in 33? How many 12s? Alright, I know that 12 times 3 is 36. But then how many 12s do we have in 33? We have 2 12s. We have 2 12s making 24. Alright, so if we have 2 12s making 24, what would the remainder be? That means 12 dividing 33 will give you 2 whole number 9 over 12. And so we can write 33 mod 12 to be equal to 9 mod 12. And we are saying that the big hand will be a 9 in the next 12 hours. The big hand will be a 9 in the next 12 hours. You can as well solve this example by saying this. You can as well solve this example using this method. 8 plus 25 mod 12 will be congruent to 8 mod 12, okay, plus 25 mod 12. Alright, okay, which will as well be congruent to all we just did was to multiply mod 12 into the bracket. Okay, when you multiply mod 12, it multiplies the bracket first, and then you have 8 mod 12, and then 25 multiplies again, and then you have 25 mod 12. Alright, and then on the next line we could write that 8 mod 12, okay, 8 mod 12 plus, I know 25 mod 12, we can write 25 mod 12 as 1 mod 12. Okay, what we are saying is that when 12 divides when 25 is divided by 12, you have 2 whole numbers and then 1 digit as the remainder. Okay, good, and that's why we write as 1 mod 12. Alright, remember that 8 mod 12 is 8 and then 1 mod 12. There is no relationship at this point because the clock has not gone one whole movement. Okay, no one rotation has happened here, and so this remains constant. But as for this, it has gone 2 rotations. Okay, 2 rotations making up 2 hours in a whole, and then that's why you have 1 as the remainder here. Okay, good. We can write this to be equal to 1 plus 9, sorry, 1 plus 8 to give you 9 mod 12. Alright, and so this is another way of doing these manipulations. we'll be looking at some other properties of modular numbers and modular operations, and then we'll be talking about addition and subtraction of modular numbers. We want to know what happens if we add the 2 hours, if we add extra hours to the 2 hours we had previously. And so on the next slide we'll be talking about addition and subtraction of modular numbers. Okay, let me simply write addition and subtraction. Okay, we're already talking about modular numbers, and I hope you understand. We're only talking about addition and subtraction of modular numbers. We want to know what happens when we add extra values into our digits. Remember that we said previously, from the previous example where we had the time is 2 o'clock now. What would the time be in the next 7 hours? Okay, what would the time be in the next 7 hours? Or we could use a new example. I could use this example, assuming we have 2 plus 5 hours. Maybe the time is 2 o'clock now, and then what would the time be in the next okay, it's better we still use our previous example from this, where it states that the time is 7 o'clock. Can I get there quickly? Yeah, this. Can we use this example to go to the page? Alright, and then we have from example 2, we want to use the same logic. Here we said 7 plus 7 mod 12 is congruent to 2 mod 12. Alright, implying that the time will be 2 o'clock at that time. Now, assuming we add 5 hours, does it have any effect on the 14 mod 12? Does it have any effect on this? Let us see what happens. Assuming we add 12 hours to the original time, sorry, 5 hours to the original time, does it really have any effect? Let's find out. Now, if we should add 5 hours to both sides, it then means we have that 2 plus 5 hours, 2 plus 5 hours, will it be congruent to adding 5 hours to 14? 14 plus 5 hours, will they give the same outcome under mode 12? Now we are considering the wall clock, and then we know the wall clock is the total of 12 revolutions, is a 12-hour counting clock. And so will it have the same effect? Let's find out whether addition affects modular operations. Alright, at this point 2 plus 5 hours will give you 7 mod 12, and then what would this give us? This gives you 19 mod 12. And then dealing with 19 mod 12 personally, what do we have? You find out that 12 can divide 19 and the remainder will be what? 7. And so it is as good as saying that 12 mod 19 is 7 mod 12. And so you find out that addition does not affect modular operations. Addition does not affect modular operations. Modular operations. Alright, over to the next slide. So what about subtraction? Could subtraction affect modular operations too? Could subtraction affect modular operations? Alright, we'll find out. Find out whether subtraction affects modular operations. Assuming like we had previously from previous example of the 7 the time is 7 o'clock and then the 7-hour time. Okay, let's find out whether subtraction affects modular operation. All right. Assuming we subtract 5 hours from both time. Assuming we subtract 5 hours from both sides, what would the outcome be? Remember, the sides are these. The sides are 2 mod 12, which we said is congruent to 14 mod 12. And so assuming we subtract 5 hours, it becomes 2 minus 5 hours mod 12. Okay, will it also be congruent to 14 minus 5 hours mod 12? All right, we find out how do we subtract 5 hours from mod 12. What we do here is this. Okay, when you subtract 2 minus 5, it gives you minus 3. Okay, you can either add 12 to the 3, okay, because there is no negativity in modular operations. Okay, you can either add 12 to the minus 3 to get the actual outcome of the operation. All right, but let's start from here, because here will give a clearer view of what I'm talking about. 14 minus 5 will give 9. Okay, 9 mod 12. All right, so how do we obtain this? Here we have to remember this operation, we add plus and the digit here is minus 5. Okay, now how do we handle minus 5? We add a 12-hour time. Okay, we add 12 to 5 because our mode is 12. Okay, whenever you encounter negativity in your operations, this is what you do. And so you have 2 plus 12 minus 5 is as good as saying 12 minus 5, or sorry, minus 5 plus 12 is as good as saying 12 minus 5. All right, 12 minus 5 gives you 7 mod 12. Okay, remember we said it's congruent to this, and from the proof you find out that it is, because 2 plus 7 gives you 9 mod 12, and is that it is still congruent to 9 mod 12 on the other hand. So all we are saying is this: negativity does not affect modular operations. Negativity does not affect modular operations. All right. And so something about subtracting modular numbers, I think you can observe from the illustration above. So from this we can conclude that all congruent numbers adding and subtracting has the same result. Okay, we can conclude. My conclusion is this. Okay, for all congruent numbers, sorry, I think I'm trying to write congruent, C-O-N-G-R-E-N-T. All right, for all congruent numbers, adding and subtraction has no effect on the results. Adding and subtraction on numbers, adding and subtraction of numbers have no effect. All right, we'll be considering something new about modular numbers too. We'll be considering multiplication of modular numbers. Let's see what happens when you multiply modular numbers. Will it have different effects on one side of the modular numbers, or will it remain the same? All right, multiplication of modular numbers. All right, multiplication of modular numbers. That's my subtopic. And then I will use this example. If 14 is congruent to 2 mod 12 on a 12-hour clock, and can we multiply both sides and get the same result? We'll find out whether we can multiply both sides and obtain the same result. Right, let's see what happens when we multiply by 3. Let's try multiplying by 3. Multiply both sides by 3. Okay, at this point you have 2 o'clock times 3. Will it be congruent? Okay, it will give 6 o'clock. And what about 14 o'clock? 14 o'clock times 3, what will it give? Remember, we can as well write 14 o'clock times 3 as 14 times 3 to be equal to 12 times 2. Sorry, 12 plus 2, not times. 12 plus 2 times 3. Okay, because we know that 14 times 3, 14 could be made up of 12 plus 2. Okay, and since we are talking about a 12-hour time, that is why we are using 12, you know, and then 2, because 14 as well could be obtained by saying 11 plus 3, 10 plus 4, and so on. But our interest here is a 12-hour clock, and that is why we are using 12 as the focal point there. All right, and then we can write this as 12 times 3, all right, plus 2 times 3. Okay, all in mode 12, all in mode 12, all in mode 12. Okay, so that means you can write 12 times 3 mod 12, okay, plus 2 times 3 mod 12 again. And remember that 12 times 3 mod 12 gives you 3 12s, you know. And then remember, when the number gets to 12, and since 12 is the central point of the even number, it turns to 0, and then it starts to count again, just like we said previously. That makes this particular line unnecessary. Makes this particular line unnecessary because it will give zeros, because it's a 12-hour time. When it gets to this point, it turns to 0. When it gets to the point again, it turns to 0, and when it keeps being 0, that makes this part of the equation 0. And then here turns to what? 2 times 3, 6 is not 12 hours, so we can say it's equal to 6 mod 12. Okay, and then you find out that 2 o'clock multiplied by 3 hours, and then 14 o'clock multiplied by 3 hours will as well give 6 mod 12. This goes a long way to prove that multiplication of arithmetic, multiplication of modular numbers does not affect the outcome. When you multiply modular numbers by the same values, okay, it will still give you the same outcome. All right, you can try further examples for yourself. You can try to find this. Okay, for the purpose of this, let me have example 2. All right, let's try to find this. 12 plus 18 mod 9. 12 plus 18 mod 9. So how do we do this? 12 plus 18 mod 9. Alright, you find out that here we are talking about a mode of 9. A mode of 9. So when the number gets to 9, it turns to 0. Alright, so we can as well write the operation as above as by adding these two numbers, but that will make the arithmetic more dicey. But an easier way of doing this is multiplying the both integers by mod 9, so that the next line turns to 12 mod 9 plus 18 mod 9. Okay, there are two 9s in 18. There is one 9 in 12. When 9 divides 12, it will have a remainder of 3, so this turns to 3 mod 9. But when 9 divides 18, it will have a remainder of 0, so this turns to 0 mod 9. And so you can write this as 3 plus 0 is 3, and so you have 3 mod 9 as the outcome. So we're working on further examples. Let's as well try out this example 3. Example 3. Could we have an operation in this manner? 3. We have operations in this manner. 103 mod 17 be multiplied. Sorry, let me make it look clearer. Come down to this line. 103 mod 17 be multiplied by 42 mod 17 to, okay, and then these be multiplied by mod 17. Alright, you have to find out something unique about this. You have to find out something unique about this, okay? And then something is unique too about this. Something is unique too about that. Alright, since you have a bracket there, remember what your mathematics is all about on board maths. We have a bracket on 42 mod 17, so that means you have to deal with the bracket first. And so you have 103 we have mod 17 multiplied by, dealing with this bracket, 42 mod 17. 17 cannot divide 42, but it can divide 34. And when it divides 34, we have 8 as the remainder, so we can write this as 8 mod 17 and then mod 17 outside the bracket. Alright, so can we take modulars outside the bracket? We can now deal with this too, because 103 mod 17, 103 cannot be divided by 17, but it can divide 102, right? And then with a remainder of 1, that's 6 whole number and 1 remaining, and so you can write this as 1 mod 17 be multiplied by 8 mod 17. Alright, and then the other mod 17 outside the two brackets. Okay, you see they both are having the same base, so 1 times 8 will give you 8 mod 17 and then mod 17. Alright, it doesn't necessarily matter because mod 17 is as good as saying 1 mod 17 times 8 mod 17, which will give you 8 mod 17 as the outcome. Okay, you can search your textbooks, get further examples, and then solve on your own. It's very simple. What are the uses of modular arithmetic? Modular arithmetic can be used in simple time calculation, just like we've illustrated here, using 12-hour time, and using the 12-hour as the saturation point where it gets and turns to 0 and starts afresh. Alright, so we can talk about uses of modular arithmetic. Okay, uses of modular arithmetic. Okay, just like I said, it can be used in simple time calculation. Simple time calculation. So we can know what time it will be from now to the next 7 hours. Can use for running task on a cycle. You know, when the cycle gets to a point, it turns to 0 and then the task starts afresh. For running task on a cycle. Okay, can be used to pick items randomly. You can use modular arithmetic to pick items randomly. What we mean by this is when you have a number of selections to make, okay, you can use modular operations to pick the selections that could be very important to you in the course of making your selection. So picking items randomly, picking a random item. Alright, so the importance of modular operations. Can we talk about that too? Let's talk about the importance of modular operation. Okay, they help us state results quite precisely and also provide a convenient way or convenient language for similar but slightly more complex statements. I think I have to write this too. It helps in precise and convenient, we put it that way, convenient presentation of complex statements in easy forms. At this point, we've come to the end of the class. Thanks for being a part of it. You have a nice understanding of it. Goodbye.